And a good morning to you all. It's a rainy morning here in Toronto, Ontario, Canada. On behalf of myself and my colleague, Dr. Gabor Lantos, I welcome you all, and there's lots of you out there, to this very important training webinar, which focuses on safe air in our school classrooms. Let me start off by giving you a bit of background information on the Bktb pilot research project, which was originally created for the purposes of the restaurant and the hospitality industries. It was specifically designed to be scalable and easily adaptable for other congregate workplace settings, such as warehouses, factories, food processing facilities, and most recently, because of the obvious need, we adapted Bktb for school and classrooms. This demand and the concern for safe air in the classrooms gave birth to the recently launched BK2 School public outreach initiative, which you are all now part of. We are pleased to highlight the fact that the BK2B project has the support of Dr. Pascal Michel, who is the Chief Science Officer of the Public Health Agency of Canada. Back to Business has brought together our own science table of a talented group, which includes epidemiologists, infectious disease specialists, former employees of the Public Health Agency of Canada, who between them, by the way, have over 100 years of outbreak response, boots on the ground, lived experience. And we also have industrial hygienists, HVAC engineers, HVAC contractors, and an HVAC remedial contractor, and many, many more. BK2B has also surrounded itself with a group of vetted service and technology providers, including HEPA filter manufacturers, lunanometer manufacturers, phone scan contact tracing manufacturers, and recently a manufacturer and developer of building air quality metrics monitoring equipment. You name it, we've got it, we've brought it together. Today, however, our focus is only on the well-being of our most important commodities, our children. Our concerns naturally also include our concern for the well-being of our teachers, to whom we entrust the care, education, and daily mentorship of our children. The classroom is our children's place of learning. Our classrooms are our teachers' workplace. They too are entitled to a safe air workplace environment. What you will hear and learn today also applies to many other interior air spaces, from hair salons to warehouses, offices, restaurants, and places of worship. Just to be clear, when we say that our goal is safe air, note that no one can guarantee pathogen-free air. What we will be discussing today is the metrics and steps necessary to remediate, limit, control, to the maximum extent possible and reasonable, airborne aerosol transfer. There are no guarantees. There are only precautionary, proactive steps to be taken. Our esteemed guest speaker, Monona Rossol, is one of the most dedicated and knowledgeable people in the area of understanding and ensuring the establishment and maintenance of indoor, safe, fresh air infused environments. This training webinar is 2 hours in length and is jam-packed with critical information. Monona's mission today is to teach us the basic principles of air movement, air management, and air cleansing. First off, she'll teach us the fundamentals and the lingo surrounding indoor air quality, often referred to as IAQ, and then Monona will guide us and help us to understand how we achieve an indoor classroom environment that is safe from an air point of view. This mission centers upon the need to achieve certain basic benchmark standards. At the end of the session, you will be in a position to confidently make demands of those people who are responsible for building air quality standards where you work. These demands will ensure that our children and our teachers are breathing safe air, and will ensure that our teachers are being provided with a safe workplace. Monona will urge you to not settle for anything less. This webinar is open to everyone. It is being recorded. There are participants in the audience from all around the globe. We do not plan on any breaks, so we hope that you have snacks and drinks nearby. If you have any questions during the seminar, please submit them through the box on the screen. We will attempt to answer as many questions as possible today, and we'll follow up after the fact with the answers to the rest of the questions, which we have not been able to get to due to time restraints. If you will attempt to, as well, specifically deal with any issues that you may raise. Ladies and gentlemen, at this time, I am pleased to introduce my colleague, Dr. Gabor Lantos, my right hand in the Bktb war room. I will leave it to the Gabor to explain the topic and his impressive past involvement with the SARS-1 Commission and his attraction to Bktb. Gabor is my right hand in terms of having supported and fostered the back to business air remediation platforms so as to ensure that everything that we do, say, and implement follow the science and nothing less. Bktb's platform closely adheres to the precautionary principle, which Gabor will also explain. Ladies and gentlemen, Dr. Gabor Lantos.
Good morning, everybody, and welcome aboard. Just a slight background of how I got involved with all this. I've been closely involved with occupational health and safety and measures, initially as a professional engineer for 12 years, and subsequently as an occupational physician for the last 33 years or so. I got involved with airborne transmission of pathogens, specifically initially with tuberculosis, and subsequently being at the epicenter of SARS here in Ontario, naturally with SARS. We made numerous implementations, depending where and when. Some were quite successful. I was part of the SARS Commission making oral and written submissions that led to the SARS Commission's recommendations of adopting the precautionary principle. For those of you who are not familiar with that, it basically means take all reasonable measures that are against the pathogens, even if all the science is not yet in. Currently with COVID, which otherwise known as SARS-2, you can see the evolution of the science over the past year and a half. There's more and more known on a daily basis, and there's still infinitely more to be known. So the precautionary principle says, adopt those safety measures that are reasonable without ever knowing all of the science. Subsequent to SARS, there was a lot of involvement, my involvement with pandemic planning over the past 20 years, trying to push the concept of airborne transmission. Not now of COVID, but even previously, the swine flu, avian bird flu, and now SARS-2 COVID. I have known Monona for about 25 years. I specifically sought her out because I had seen her expert work in the field, in what I was involved with and doing, and recognized her, myself, as do others, that she's an outright authority in her field of industrial ventilation, which is opposed to quote unquote air conditioning, which deals with heat, cold, energy. Industrial ventilation deals with trying to get rid of the toxic environment, be there chemical, be there particulates, be there whatever. She has written numerous papers, books, presents regularly at conferences. She's an internationally known consultant, and recently she's an advisor to the American Council of Government Industrial Hygienists. She will focus in this talk, mention others, but focus at what I mentioned as industrial ventilation, as opposed to what we commonly know as air conditioning, which deals more with comfort than detoxification or purification. It is my pleasure to welcome Monona Rossol. I'm sure you will find this presentation both informative and educational. Thank you.
Okay. I'm going to assume that everybody can hear me and that they can see the slides. We'll be going through this, and I just a moment of bias that you need to know. I've been a union member since I was 3 years old, so I really truly believe in the union position that we have to unite as workers. So if my bias bothers you, just cancel that part out and just listen to the technical stuff. But I am definitely pro-worker to a fault. So we're going to look at ventilation. I looked up some of your regulations. I noticed you have the same kind of basic regulation that says the employer shall take every precaution reasonable in the circumstances for the protection of a worker. We have a similar clause in our OSHA regulations. It's called the general duty, and it's very similar. Let's look at the Ministry of Labor advice on ventilation for COVID. And this slide presentation is going to be available to you to download a copy. So you don't need to do screen sharing. You can just know that you're going to get the whole shebang. And whenever I quote something, I make sure that there is the reference that you can see this same quote as well. And what they say is that you should keep windows and doors open as much as possible. Make sure that you're using the temperature control and fans as safely as possible. And whenever possible, make sure that outdoor space is available and consider going beyond minimum standards if possible. That is the wording that we also see here in this country from our Centers for Disease Control. And the translation is, consider exceeding minimum standards and take other precautions whenever possible. If it isn't possible, open the building anyway. I'm sorry, that does not fly. And we should not be accepting that. The workers should take the risk rather than requiring employers to fix the ventilation. Okay, and who do you trust for ventilation advice? Just think about your doctor, a man who has no idea how the HVAC in his own office works. Why would you go to the medical experts in the health agencies? It just doesn't make sense. That's not where you go for ventilation advice. And it was only recently. I'm so unhappy that they didn't even realize that this bug was airborne until very late in the game, both your country and mine. Oh my gosh, it was so obvious right from the beginning. And when they asked when we should have known that the virus was transmitted by the HVAC, and I answer in 1962, because tuberculosis ward studies made it clear, this one in particular, absolutely conclusively demonstrates that the TB bacillus comes through the HVAC. And this thing is, if we're sneezing and we're coughing and we're putting particles out, obviously they can go through the HVAC. There's nothing to stop them. So we should have known. And anybody who has ever been admitted to a hospital knows that the first thing that they require is a chest x-ray. And that's based on their knowing that the HVAC distributes the bug. And so they're going to put you in a special room if you have TB. So in addition, there's many early pandemic studies showing clearly that it's transmitted. So I don't know why they didn't start to function with this advice right from the beginning, because we certainly did. I'm the safety consultant for SAG-AFTRA and a number of the other unions, theatrical unions, and they put together 11 experts and we did a plan. I was one of the experts. And so the film industry has been open all through the pandemic. And it's because we do have proper testing, proper masking and distancing when possible. Remember, some of our people are paid to kiss each other. So we have to have good ventilation and other precautions as well. So I went to your building code, and I was gratified to see that under good engineering practice that you should be looking at, they list the two agencies that we're going to look at today for advice. ASHRAE, and you're going to learn what these acronyms mean, and ACGIH, the Industrial Ventilation Manual. These are the two basic standard setters, the international ones, because people from all countries can be on them. So let's look at who they are. ASHRAE has about 6,000 Canadian members, student branches, chapters, and so on. And its name means the American Society of Heating, Refrigerating, and Air Conditioning Engineers. Do you see anything in there about control of infectious aerosols or health standards or particulate? No, these are comfort people. They set up the systems to provide reasonably good air and of the right temperature and humidity so that people in the building don't complain and they can function well. And they've been strictly a comfort ventilation group for decades. And since I've been in this business a long time, in the 80s and 90s, anything that had to do with toxic or hazardous issues, they referred to ACGIH. Okay, that's the next one we're going to look at. And that's the American Conference of Governmental Industrial Hygienists. And again, it's open to people of any nationality, as long as they are employed in environmental health in at least 50% of their time. And industrial hygiene deals with toxic airborne substances. That's what we've got here. And your building code refers again to air contaminants. And it says that they shall not be permitted to accumulate in concentrations greater than permitted by the ACGIH, and they refer again to the Industrial Ventilation Manual. We will look at that manual. And the levels that they refer to are the threshold limit values. Now, I'm going to assume that people sort of know what these TLVs are, because they should, if they've had WMIS training, have had information on the occupational exposure levels, the OELs, for your area. And these are the amounts of substances that are allowed in the air for healthy adult workers. That doesn't apply to young students or people with asthma or other health issues, but it is for healthy adult workers. Okay. And how long have I been involved in this? This was the first ventilation award I got back in 1984. So I have been doing this for a very long time. Okay. Let's thank you for talking about my favorite stuff. And it's easy to talk about it now because there's so many wonderful places to steal slides from. And one of these is a French study that I've listed here because it makes diagrams, and it makes it very simple for lay people to understand. So the first issue they talk about is, you know, when Typhoid Harry comes to visit the home, and what happens in that private home. And what they show is that if there are no precautions, that everybody in that room, all 5 of them, are going to come down with this bug. And now with the Delta virus, that's even more assured. If they all wear face masks, they might protect one person. Remember, those face masks, those cloth face masks, those are for protection of others around you. They cannot stop the bug. So unless you're wearing an N95, this is a kind of weak protection. And then they say, but if you ventilate the space, then maybe you will only pass it to one person. And that's just even a maybe. And this is their arrow up here coming in the window. And they have left this door open. This is my arrow that I added, because unless you've got air ripping through that room, nothing is going to happen, because that window cannot push air into a space that is already full of positive pressure. You can't, not unless the room is made of rubber, okay? And ideally, you would like the door over here so you would get a diagonal through the people. But this is important to understand, that ventilation involves air movement, okay? So if you close this door, I don't care whether you've got that window open or not, you got 5 pieces of toast in that room when the 4-hour visit is over, okay? This is directly from the WHO document on ventilation, and this is their first graphic, not these arrows, they're mine, I added them. But they say, open a window and all will be well. Yeah, right. And then they have the little arrows going out at the top, coming in at the bottom. That tells me that it's winter outside or cold outside, because the cold air is coming in at the bottom and the hot air from the room is going out at the top. If it was summer, those arrows would be reversed. And if the air on the outside of this room was the same temperature as the inside of the room, there would be very little air movement, just a little diffusion right here, because there's no impetus for the air to come in and to go out. Air doesn't just look for a window and say, that's where I want to go. There's got to be a reason for it to go. Even more important is the prevailing wind. If there's positive pressure blowing air at that window, you got a pretty good chance that there's going to be turbulence and air movement in that room. But if you're on the negative pressure side, there may be no movement at all, that there may be nothing seriously happening. So it's weather dependent. And ASHRAE, in their first document after the pandemic got really a hold of us, and that's April 14th, 2020, they recognized this and the other issues, and they made it clear that airflow in buildings where you have windows as your protection provide variable and unpredictable air patterns, and ability to actively manage risk is much reduced. So it is important to understand that windows are never the solution. They might help if the weather is right, but there are limits to this, okay? Now we have to understand the particle that we've got to move. And originally they were talking only about sneezes and coughs, singing and playing instruments, but just breathing through the nose can also produce these particles. And they come in 2 sizes. We're going to look at them in terms of size, the aerosols. Sometimes they call them aerosols, sometimes they call them depleted nuclei. They got a number of names, but the droplets are the big ones and the aerosols are the small ones. And the louder you talk and yell at people, the more you're giving them the business. So this is a good slide to send somebody that you want to tell to shut up and leave you alone. And you need to understand that in still air, and we're going to look at a number of still air studies because they were the ones that came out first. And I want you to know you've never been in still air. As soon as you walked into that room, you created air currents. And most rooms are full of movement of one kind or another. But if you're in still air and you're infected, you start to spread this bug. It slowly disperses, and you'll notice it disperses everywhere, given the right amount of time. And that rate of dispersion is based on particle size. And the particle sizes that we are going to use, because they're the most effective way to look at this, are the same ones you would have learned if you had a good WHMIS training. And the first group are the inhalable particles, from 10 to 100 microns. Those are the ones that are big and heavy and deposit in the upper respiratory tract. The respirable ones are under 10 microns, and they deposit in the lower respiratory tract. Now you'll notice I'm using the word microns, and I abbreviate it as this Greek mu. Now I know that right now that a little mu is the way to do it according to the International System of Units. But I'm an old gal, and I learned this long before this, and it was just the U when I was in school. So I'm just going to use it. It saves time and space and typing. So get used to it. This is microns, okay? The nanoparticles are much smaller, and molecules are even smaller than that. We're not going to have to worry too much about these because the virus itself averages in diameter 0.125. Now, there are viruses that have been seen that are much smaller, even half this size, and double its size. So it varies, but this is considered the average size of the virus. If we look at a graphic that represents the different things that are respirable and that can get down into your little air sacs in the lungs, this is PM10, this is PM2.5. Those are the two that EPA monitors. Here's your big fat TB bacillus. And here is the COVID virus, this little bitty thing. And here's nanoparticles. And of course, you can't get small enough to see a molecule. So we're probably just going to refer to gobsmackers and aerosol in most cases. And the gobsmackers are the big ones. And you see in this still air study, somebody who sneezes or talks loud or does something and really just gets this poor sucker standing in front of them. And then you'll see that the big gobsmackers end up going down, and some of them end up on surfaces, in this case, the floor. The little ones just keep moving out and out and out, and pretty soon they fill the room from dispersion. That's the picture you want to have in your mind. The longer you're in a room with somebody who's infected, the bigger the problem can be for anyone that's in that room. And you already understand this if you just think a minute. If somebody throws garlic in a pan in the kitchen, and you're in the bedroom, you're going to smell that garlic so fast, you're going to know that they're cooking. And that's because molecules are so small, they disperse really fast. So the CO2 from your breathing is also going to go very fast through the room by dispersion. But if the garlic catches on fire and makes aerosol-sized smoke particles, you're going to see that rising from the pan and then spreading through the rooms and finally getting to the bathroom. And that is more like the movement of the aerosol particle. And you can predict how the gobsmackers are going to fall with Stokes' law. It tells you how fast it will move downward, but that is in still air. So it does not predict how the particle is going to deposit in your room, because that is going to depend on many, many other things. And I've circled this guy's name. You're going to see it several times. He's not the greatest researcher. He's just a really, really good one. And he writes in a way that people usually can understand. So I'm going to refer to him in several studies. But this is the Stokes law study that talks about things depositing. And if you look at this graphic of what the aerosol might look like, and you see the bug and you see it's in a liquid, that liquid is either saliva or it is lung fluid, depending on where the particle was generated in your respiratory system. Now, if you know anything about water and you see a surface area that large, you know that that's going to evaporate really fast. So that is your other problem. And that is that the gobsmackers end up being much smaller. And you also need to understand that this is not just water. If you've ever seen spit dry, you know that there's mucus and other stuff in there. So the virus kind of coats itself with the dried desiccants of your respiratory or your mouth saliva, and it protects itself. So they can stay alive quite a while in the air. Even the big gobsmackers can end up quite small. Okay, and that process is dependent on humidity and temperature. The lower the humidity, the higher the temperature, the more of the aerosol you're going to be producing. And the longer they're going to be airborne, because they're going to be affected by the speed at which they're emitted and the air currents in the room. And the smaller the particle, the longer it can linger and stay in the air. Okay. Now, if you remember anything again from your WHIMIS training, you might remember that this size particle is really hard to capture, 0.3 microns. Whenever you look at the performance of a filter for fine particles, you're going to see that there's a dip right around that range. And you should know the reason why. When a particle, small particle, intercepts a fiber in a filter, it is not captured like it's a sieve. It's captured by touching or banging into a particle. Then the van der Waals forces between those two small particles will cause them to stick together. Okay? If they're really, really small, they have a very circuitous route because they're being bombarded by atoms and they're being kicked around, and they have a really good chance of hitting a fiber also. So these filters are very good at catching the big stuff, and they're good at catching the really small stuff, but around 0.3, they have an aerodynamic capability of traveling around the fibers on air currents. So they need to have a positive charge on these fibers. It's built right into the polymer so that these special fibers then can attract the particles that are in that size range. Also, you're going to see 0.3 being talked about over and over and over, and so you might as well know that some of the latest information is beginning to show that it really probably is more in the range of 0.12 to 0.17 that this dip occurs. And I want you to know that because you're going to see charts like this one. Here's your 0.3, and why are these all over here? Well, this is the newest data, so don't be thrown off by that. But anything that is right in the range of where our bug starts in size is where it's really hard to catch the little suckers, okay? So how long will they stay in the air? They float in the air currents, and there's a number of studies showing 2 hours, 3 hours, and still being effective. But there's one study, and it's on the CDC website, and here it is. It was done at Tulane, and they were effective and demonstrated to be effective after 16 hours of bouncing around in the air. Is that common? We don't know. But don't assume that they're just going to die somehow out there. They're not. Droplets and aerosols can be generated in the thousands, and one infected person obviously puts multiple people at risk. And this again, here's our orange juice guy, Tang. And this was, he made it right clear in one of his papers that it's the momentum with which the particles are expelled, the characteristics of surrounding airflow, speed, turbulence, direction, temperature, and relative humidity that determine this. All right, we're done with that. Let's look at barriers, because there are people who think they work. Okay, now this is a study that was out, and it was showing that if somebody coughs or sneezes, that things aren't going to go well for the guy across the way if the barrier isn't tall enough. And I mean, he's really going to get a face full. So they raised the barrier 20 centimeters, and now this guy doesn't get hit by much of anything. But what they're not looking at is what happens in the cubicle where this guy is coughing and breathing, because it just builds up and builds up here. Every breath is adding more, and there is nothing to stop it from going all over the freaking room. And here again, the analogy to smoke works best. This study shows it just, this smoke is, it's not, the barriers just can't stop that small particle at all. And in some cases, here's a lunchroom where they put a barrier between the people on the table and then between each of the people sitting at the table. So there are 4 chairs here in the space. And you've got people, if one of those people is infected, there's 4 pieces of toast in there by the time lunch is over. It just traps what they're producing. Okay. So, and here I've given you a study that you can read and look at, and it not only shows that that the risk reduction is not as high when you're looking at desk shields, it may even increase the risk. These are the ones that work, that are in your bank, for example. If they go floor to ceiling and there's different ventilation outlets on either side, this is quite effective. But barring this, this is not where you want to go, okay? And people keep talking about outdoors being good. And this is a study that someone did about walking in a corridor and walking outdoors where there's more dispersion. And it's quite helpful if you just visualize what happens when you're outdoors. When you're indoors, there's no place for this to spread, so it stays concentrated longer after more steps. But outdoors, it gets quite diverse, quite thin, and it reduces the risk of infection. Okay, here's our French study again, and this section should have been titled "A Man Walks into a Bar," and he goes in, and there are 15 patrons, and the windows are closed. And after 4 hours, if no measures are taken, 14 of the 15 customers will be infected. This might be an admonition not to stay 4 hours in a bar, I'm not sure, but that's probably pretty close to right. If everybody wears a mask, now you're cutting it to almost, not quite, but in half. But then they say if you ventilate the space, maybe only one person's going to get it. But I don't know about you. I'm not saying I've worked in a lot of bars, but I've never seen one with an open door like that. And I don't think anybody in New York could keep the back door open that far from the till. So, and then they say there's air coming in here and going. Obviously, they don't know what they mean. They just say if the air is turning over very rapidly, there's going to be less. And that's probably right, but we need more than this. So we need to really define ventilation and the 2 types of systems, the ASHRAE and the ACGIH, because we're looking at comfort systems for buildings that are in most of your buildings. If they have what's called an HVAC system, a heating, ventilating, and air conditioning system, and industrial systems if you're in a shop or a laboratory or something like that. And this is a drawing that I've marked up because it shows the difference. This is recirculating ventilation that's in most offices, and this is a single hood going to the roof. And these come under 2 different systems. Okay, this is the ASHRAE system. This is the ACGIH. Okay. So I'm primarily, obviously, in the ACGIH camp because I've done about 80 buildings, and that's the part of the building plan that I deal with. And I deal mostly in terms of art and performing arts buildings, theaters, places like that. If you work in a laboratory or shop, you may already have ventilation that's good because some of those labs have 8 air changes an hour. That's even more than the minimum that we recommend. So you need to look at where you're working, if this even applies to you. But if you work in a building that says we're compliant with code, we follow ASHRAE, and we meet all those standards, they are telling you they do not have sufficient ventilation. And who says so? ASHRAE says so, okay? When they put out their document, they looked at this standard that provides ordinary ventilation, and it's for the purpose of removing dust from outdoor air, primarily to protect the HVAC system. So that means they get some PM10 and some PM2.5, but not much. They provide enough fresh air to dilute the CO2 from your breath, and they're energy efficient and low cost. None of those objectives are going to help you one damn bit, okay? So the reason is your breath is now the recognized hazard. And that's why, again, I go back to this document, April 14th, 2020, ASHRAE put out new guidance, and they said, you gotta modify the HVAC system if it's gonna be safe for this bug, okay? And this is their schematic drawing of typical HVAC system. We're going to actually look at parts of it. This is the section that they tell you we have to look at first. This is your demand control ventilation system that is based on CO2 readings. And this is the energy recovery unit. In the States, we usually call these heat recovery units, but whether it's ERU or ER ventilation or heating, it's the same kind of creature. And they have been my bane in good buildings because these things leak. They were designed to leak. If you break this down, they get the drawings for these heat wheel systems, and look, you will see that there is a point at which the exhaust air and the fresh air coming in pass each other with no barrier between them. I mean, you don't have to be a genius to figure out that that is going to cause exhaust air to return to the rooms. It just doesn't make sense in terms of industrial ventilation at all to use these. So if we are going to do any kind of energy recovery or heat recovery, we want to be using these glycol loops because these suckers leak and you end up with a bug coming back. And your home may have one. I was amazed to see that the Ontario Building Code has been revised to require heat recovery ventilators in all new homes. And even if your home is older, these HRVs will really improve air quality. They say that is dead wrong. They can't improve air quality at all. All they can do is recover some heat. So I have a problem with that particular rule, but as you can probably guess, I have a problem with a lot of things. These are the demand controlled ventilation sensors, and they turn the system on when the CO2 gets high enough. And ASHRAE says in that April 14th document, disable that sucker. Either that or change the set point to the ambient CO2 outside, which means your system will not turn off because it's going to always be too high. So if we go back, we'll look at the reason. Remember these where the bug is dispersing, and we know that the gas molecule is really small and disperses fast. and the SARS aerosol's a little slower. And this is a picture of a typical handheld CO2 monitor. If you follow the ASHRAE 62 indoor air quality rules, your level is 700 parts per million or less above outdoor levels. And that would be when this system would kick on. So you could be measuring levels of 1,000 to 1,200, and that would be okay with the standard, but it's not okay now. Okay, and the reason is the CO2 that you measure indoors minus the CO2 you measure outdoor, ambient, equals the amount of CO2 you just re-inhaled from either your own or someone else's lungs. That is not what you want to be breathing. So the risk of infection, because of the difference in dispersion rate, is not exactly proportional to the CO2, but it is related. And CO2 levels do increase the risk of infection. Okay? So a test that some people are proposing is that you limit the total to 600 parts per million, so you'd only be 100 or 200 above outdoor. But that's going to require really great ventilation to achieve, and that's what we want, really great ventilation. So now let's go back and let's look at the business end of the HVAC system in your room. You're going to actually know where the air is coming in, where it's going out. If the air is coming into this system, it makes a UE and it goes to the filter. This is a very low grade filter if it's meeting the ASHRAE 62.1 standard, because it's just to protect the machinery here and catch the big, we call them crumbs, flies, and feathers filters because they just stop the big stuff. And now the air comes through, and I cannot tell you what a bad idea it is to bring the air in at the ceiling and take it out of the ceiling. That's just really, from a point of view of air exchange in a room, really not the best idea at all. And in this case, if this guy is infected and you get some of his breath and it's going back into the return in the room, when it gets here, you could exhaust it. That would be good. Or it makes 2 UEs and goes back through the crumbs, flies, and feathers filter and back into the room. Not a good scenario. Okay? So, some of the better systems, this was in an engineering magazine, and I love it. It puts the air coming in at the ceiling and takes it out at the floor. That guarantees that the air is going through your breathing zone. And if there's an aerosol in the air, it's aiding in the downward deposition direction that you want. ASHRAE's floor to ceiling systems bring the air in at the floor and take it out of the ceiling just to take advantage of the little warm air currents that you make here. But this system could only have been designed by a bunch of men sitting around in a room who have never pushed a vacuum cleaner. It just doesn't make sense to go in that direction. And that upward flow will keep that virus suspended indefinitely. Here's what you see in your ceiling. This is called a diffuser. This is where that mixture of indoor and outdoor air is coming in. Remember, that's not fresh air, that's a mixture. And this, of course, is a building flaw. You wouldn't have your return this close to the supply. Okay, but that's what you should be looking at, where those are. And anytime you put the supply and the return on the same wall, and I don't care if it's on the side or whether it's on the ceiling, it's not a good idea. And one of the reasons is if you make this air really, really have a slow dribble into the room, then it just travels from one to the other. You've got dead air here. If you blast it in so that it gets all the way to the other side of the room, your dead air is here. But no matter what you do, if the intake and the return are on the same surface in the room, you're going to have a lot of dead spaces. And that's why the pandemic was an exciting time for someone like me, because now we've got all kinds of gas tracers and things where we can actually show from empirical tests what is happening to this airflow. And you can see they're throwing it in here. It's going across all the way to the front of the room and out the outlet. This is a patient room where there are 2 beds. And these people are obviously creating the bug and putting it in the air. And when they look at bed number 1, there's some of this that doesn't make it out. Some of it goes to the outlet. But bed number 2, that aerosol that they're creating never makes it out of that room, because it just gets in a dead airspace and circulates. So it's really important now to know where the air is traveling in the room. And now I'm going to take a hit at these people. I mean, I'm not going to have any friends left at all when I'm through with this. The Harvard Healthy Buildings Program, I do not subscribe to their ideas here. As far as I'm concerned, those are all lousy, not good. This is even worse, because you're likely to just be dragging the air from there to there, and now you've got an even bigger dead spot. And this is a dilution ventilation pattern. This is an industrial direction. And here again, you can see what ACGIH draws, their pictures. If you've got the air short-circuiting between the supply and the return here, then you're going to have a dead zone here. If it's at the ceiling, you're going to have a dead zone down here. And they say this one is a good one, and it is. You bring it in at the ceiling, you take it out low. That works a lot better. So you also want to know where the damn air is coming from. When you see this diffuser, be aware, if you take the ceiling tiles off, like I've done here, there's a duct bringing that from somewhere. So let's look at where the air comes in from. And architects are notorious for taking all the ugly stuff and shoving it in one tiny location and hoping nobody goes back there, so that the building can all be beautiful from all the other angles. This is a loading dock, so the trucks sit and idle here. Those are the intakes for the building, and they're going to pick up all that exhaust. Here's the trash fulminating. Here's the door that the workers come out with and stand on the platform to smoke. And if they've got COVID, that smoke and the bug are going right up in there. So you really kind of want to know, where's the air in my floor coming from? The other area where they really get into trouble is on the bloody ceiling. And I mean, on the roof. These are air handlers. They bring in large amounts of air and then distribute them in lower floors. There's 2 of them up here. But all these other things are also expelling stuff. This happens to be chemistry fume hoods. So you can see that whichever way the wind is blowing on a particular day, you're going to get stuff into the air handlers. And what you can't see is all kinds of little pipes, low, real low, that are the bathroom exhausts. Oy, you don't want to do this. You need to get stacks. You need to get them up into moving airspace. But architects, again, they've got design concepts, and they don't want anything making the roof look like it's got stuff sticking up from it. They've got pure lines and issues. Well, I've got issues too, as a matter of fact. Then if you look into the ASHRAE standard on how much air you want to bring in, your outdoor air rates table, this is the table that drives me crazy. Because, for instance, they have music and theater and dance. They have all kinds of this. I just put down a few of these, but they've got pages of them. And they say an art classroom. Now, I'm going to tell you, because of what I do, you cannot set the ventilation for any art classroom unless you know they're using crayons. It depends on the materials that they're using. But they've said, no, it only needs 10 cubic feet per minute per person. Ridiculous. Ridiculous. It depends on the toxicity and the amount of toxic materials that person is using. Let's take the worst example I can think of. Now, don't get me wrong. If I hadn't been listening to this guy, I wouldn't have gotten through the pandemic all night, because he just tells me that the trees are happy and the mountains are happy and here's a happy little sky. And I got through the pandemic. But he talks about his wet canvas. That's wet with a petroleum distillate solvent. And there's plenty of that on his palette. Here's a whole can of petroleum solvent. And he dips his brushes in there and shakes them into a container over here and slaps them on the easel. And he laughs about the fact that he's spraying the crew. I'm going to tell you, you cannot get worse than this in terms of exposure to solvents. And there's no way that 10 CFM is going to come anywhere near protecting him. And during the pandemic, CFM per person just won't work at all. If they're telling you how many CFM per person they're getting, you say, no, we don't even want to go there. We're done. We want to know something else, and we'll tell you what that is in a minute. Because if you have two people standing this far apart, and one of them is Typhoid Harry, I don't care if there's only 2 people in that room or there's 20 people in that room, the risk is the same for transmission to this guy. Okay? So CFM per person is not going to help. You get all this extra CFM, it's just really not going to help this guy. Okay? Instead, and we also need to look at the other part of this table, the air class. And that's where ASHRAE actually takes themselves out of the running for dealing with this problem. So you see their air classes. There are 4 air classes. I'm just outlining quickly of inoffensive, mildly offensive, and offensive. You can read the full definitions when you get the PowerPoint. But class 4 is highly objectionable, potentially dangerous, with particles, bioaerosols, whoops, there's your bug, at concentrations high enough to be considered harmful. Bingo. And class 4 air shall not be recirculated or transferred into any space or the space of origin. So essentially they've said, our standard can't be used, okay? Because it's a recirculating standard. If you've got a contaminant of concern, you're supposed to go consult with a recognized authority, a cognizant authority for dealing with it. And that's not ASHRAE. Now, for decades, all through the 80s, all through the 90s, that cognizant authority was identified as ACGIH. But now they've relegated ACGIH to a footnote in a table. So they think they can do it all, but they can't. Okay, so let's look at their April 14th requirements for non-healthcare. That's everything other than healthcare, apparently. And they say, flip those dampers open to 100%. So you're getting all of the air that's going through the building exhausted, okay? And if you're going to use a filter, it's got to be MERV 13 or the highest level achievable. Keep your systems running 24/7 if possible. Add portable air cleaners with HEPA or high MERV filters. They also talk about UV, but we're going to talk about why we don't think UV is a good idea at all. Maintain temperature and humidity and bypass the energy recovery systems, which we talked about. Okay, that's their rules now for non-healthcare. If you look at their healthcare regulations, we don't need to go over all of these with pressurizing and 100% exhaust and all that, but this one is important. Increase outdoor air change rate, because now we're getting to what we need to be looking at. In patient rooms from 2, which was their previous recommendation, to 6, because they understand, as do most of us, that about at 6 air changes, you can begin to control these aerosol size particles. So when you take an ordinary HVAC system and you increase the air ventilation rate by disabling the demand controlled ventilation and flipping that damper over to 100%, you no longer have an HVAC system. You have an industrial dilution with very poor location of supply and exhaust. Now they're in my playpen. So now we can look at ACGIH and American Industrial Hygiene Association, OSHA, and other standards. And this is the Industrial Ventilation Manual that is recommended in your code as a design standard for industrial. Don't ever think that this is anything to do with ventilation. Fans are not ventilation, they are turbulence. And whenever you see a fan sitting around, that is nothing, okay? That is nothing. All righty. And this was taken by a New York teacher. They said, you've got good ventilation. They had piled a bunch of chairs near the window, stuck an ordinary fan there, and opened the window a few inches. I'm sorry, that doesn't cut it. Because whenever you have a fan like this, there's positive pressure in front of the fan. There is negative pressure behind the fan, and you have major recirculation going on around this fan. It is not good ventilation. You might feel some turbulence in the room, but you're not getting air just ripping from this window into the building. That's why real exhaust fans have a template that goes around so that it can't recirculate, that whatever goes through the fan goes through and stays on the other side and can't come back, okay? And if you compare HVAC engineers with industrial ventilation engineers, it's why I have so much trouble when I'm talking the building. I won't go through all these, but just take a look at the duct velocities. This is the duct velocities that the HVAC people work, and we start at those numbers and go much up. When we tell them we want 5,000 feet per minute at the center line, and we tell that to an HVAC engineer, his eyes dilate. He has no idea. We operate on entirely different scenarios. So it is a different kind of ventilation. And we have two basic types, dilution or general ventilation and local exhaust. And we'll define them both for you. And a basic dilution ventilation, you bring air in, you contaminate the air, and you yank that air out. Now, obviously, in the winter, you'd freeze your tail. In the summer, you'd cook. So you have to have special things that make the air come in at the right temperature. But you're driving the air through the space in one way or another. And by the way, this is the wrong application. This should be local. And I love this slide because it's from an ASHRAE training package from years ago. So they didn't get it then either. Okay. So here's a makeup unit. It yanks air in and cools it and blows it out at the same rate as it's being yanked out by other systems in this shop, okay? And here's an exhaust fan, and I deliberately used one with a lot of dirt because this takes about 50% of your fan's power. When you have things blocking this fan, it does not operate well against static pressure. So you cannot be blocking it with any kind of material. It has to be free to do this. This is a typical ceiling exhaust warehouse configuration. You bring the air in low, you take it out high. Could be better in direction, but we'll go for that. And this is the formula that we would use to calculate the rate at which we would need to be using ventilation for a contaminant. And since I deal with solvents a lot, if you were hiring a firm of architects that I was consulting for, then one of the first things I would do is to talk to the people who are using the solvent. Let's say they're painters. And we would talk about those threshold limit values. The important thing to remember here, and I mean, don't get panicked, this is a formula, but the only thing I want you to know is this threshold limit value, which is like your OELs. The smaller that number, the more toxic the stuff is by inhalation, and the less you should be breathing. And the important point of my showing you this formula is the TLV is in the denominator of that equation, which means the more toxic the stuff, the larger the amount of CFM, cubic feet per minute, ventilation you need. So what I would usually do would be to take two solvents. Say they were crazy enough to want to use turpentine for their painting solvent. We would calculate for a classroom of a particular size and number of students, how many CFM per person they would need. And if you're using a good petroleum distillate that is for painting, it comes out to around 200 CFM. And if you're using turpentine, it's almost 1,300. And it's not sustainable. You really can't do that. So if you take a look again at our friend Bob Ross, and he's using, in my estimation of watching him night after night after night after night, he's using somewhere between 5 and 10 ounces of 100 part per million TLV solvent in a half an hour. So he's going to need about 4,000 CFM, somewhere between 2 and 4,000 CFM, depending on what painting he's doing. Not sustainable. He needs to be in a wind tunnel. There's another problem. Many solvents don't have TLVs. We know they're toxic. We know they're toxic because solvents in the same class are very toxic, okay? So we have really good reason to suspect that these are very toxic too. And that's when we have to look at the same issue for our virus, because we don't know how much the infectious dose of this virus is. And then we have to use the precautionary principle, which says we want to really capture it well. We do not want to be breathing this stuff. So we want to operate on the side of caution. So this is a subset of ventilation called displacement. And what it basically is we don't care what's happening to your feet. Feet have never died from solvent exposure. We also don't care what's happening at the ceiling. What we care about is the breathing zone. If we can put the air in and take it out where the breathing zone is, then we can reduce the amount of air we need and we can be more efficient. Here's drawings by other people showing the same kinds of issue. Oh, shoot. Here's from a ventilation manual showing to configure. This is not good because you get turbulence in the right angle bend, but this is nice. Goes right straight across here. Here's a diffusion type where it's coming through a large area, and because there's a heat convection current, this goes up. But this is, of course, not realistic because you're not going to be ventilating for one person standing there. You have to look at all kinds of configurations. But this is one of the buildings that I did the I-8 for that won the AIA Code Award. And these are diffusers. There's a positive one and a negative. So we're not going to exchange all the air at the ceiling. We don't really care. If that's bad air, muzzle tov. But we're wanting to make sure that down here, we're getting a sufficient air movement. Here's other pictures from the same building. And these are the perforated diffusers. They come in all different kinds of shapes and sizes. And air can either come out of them or go into them, depending on how you want to use them. This is another system we use for painting racks, which put out a lot of solvent when, excuse me, when the paintings are drying, and you put the casework in front of the plenum. Here is when it was being installed, so you can see all the little holes. There's negative pressure behind there. So air is being drawn through this all the time. So if you supply at the other side of the room, then you have air going across. And this was from a study. Oh, I don't have it, but if you ask me, I'll find it for you. But this one is a kind of a thumbs up one. These, forget them. But here they're blowing air, fresh air, right at the people. and they're taking it out up here. So you're creating an air current like this, and that will work. But that's getting toward local exhaust, because that's the other major area of industrial ventilation. And that's when we capture the stuff at its source. This would be a grind wheel, table saw, spray booth, that kind of thing. Needs a hood, duct, air cleaning, fans, an exhaust exchange, makeup air, so on. And you cannot be using this kind of fan. Propeller fans cannot move those at all. That's important because they're running around telling you this will work. You just take a MERV 13 and stick it on a box fan, and I don't care what their numbers are, can't work. Just can't work. And if you go and Google this guy who did this and follow all of his papers, starting with the one that we just looked at that shows the fan and the filter stuck together, and then he figured out, oh, there's recirculation at the corners, so you got to put this template on it. Oh, there's too much resistance. So he ends up with a system that has 5 MERV 13s. There's a MERV 13 under here and 4 around the side, and you got to paste it together. And these filters are only guaranteed for every 3 months. So every 3 months, it's going to cost you $175, and you're going to have to unpaste them and redo them. I don't think that's really viable. This is the kind of fan you need. This is the fan. It's called a centrifugal fan, and this will shove air with resistance in the ductwork or wherever you have it. It's the workhorse of our business. It's also important to know that wherever you draw air, it only draws from a few inches away. When you blow air, you can feel it at a great distance. But don't think that all of the air that's coming out here ends up here. That's not what happens. Think more in terms of somebody blowing smoke rings, okay? That's what's really sort of happening. So there's some of that air here, but it doesn't just take air and move it to there, okay? This is a diagram of a local system, and we're going to look. You have to know that if you're designing ductwork, you don't want anything that suddenly changes the size. It's got to be gentle. You want the curves to be gentle. You don't want right angles, and you never want to see right angle entry if you can avoid it. And I love this slide because it was in a state training package saying how to do it right, but it's how to do it all wrong. Here's right angle entry. Duct is changing size too fast. That's too tight a bend. So here's a really beautiful one. I'm happy if these ducts enter at a 30-degree angle, but here they've actually curved and put them in so they're smooth. When I'm depressed, I just put that slide up and I'm immediately feeling better. Here it's all wrong, right angle bend. They spent money on welded stainless steel, all wasted, doesn't work. And here is right angle entry, too tight a bend. And I want you to remember this because we're going to visit it again. Okay, just look at that. Okay. You also should be obviously aware that's not going to work. And then we go through all kinds of formulas about how far away things can be from capture, how to improve capture, where you put stuff in order to get it captured. If it's hot, you put the stuff above. You never want your head between the vent system and the source, really dumb. Cross drafts, these kinds of overhead systems are only good if you have heat. If there's no heat, that's ridiculous. That's a foundry. This was in a theater die shop, and when I came in on a consult, I said, you know, you just put this in, you need to call your lawyers. Because remember, these systems only draw from a few inches away. This has absolutely no effect on this at all. None, zero, totally wasted. Here again, what were they smoking? It doesn't even get this guy's dandruff. It's too far away. And here's what I wanted you to remember, because they were telling people, and they supposedly have numbers, and they're just plain wrong because this can't work. they say this guy's bug is all going up here and going in the system and out. Not happening. Here's another shot of it. Absolutely not happening. Okay. Then we got to figure out where we're discharging them. And remember the roofs. I said we would be revisiting the roofs. And if you put it too low on the roof, it re-entrains from prevailing winds. That's why you've got to stack. You've got to get it up. And this is where also the bathroom vents go. They go into what's called black water vents, and they go to the roof. You can also exchange from one to the other if water is not in these drains, and they can pick up stuff. And this was from a study in Korea where building transmission was assumed to be indoors, but they now think it was actually from the roof. This is a 2004 studies of SARS-1 in Hong Kong. And the data on who got it, see, the yellow building was the building that had the infections, and the gray buildings didn't have infections, but the people in the apartments adjacent to where these go, and you can see this is a 90-degree angle change in view, those apartments got the bug. And it is perfectly consistent with fluid dynamic studies of prevailing winds. Now there's also a study that shows that it might have had to do with the fact that they have exhaust fans here, and they could have been passing it from building to building. And they plotted the data. And the data on the outdoor route model fits the data best. These studies are here if you want to read them. I find them fascinating. You may find them an encumbrance, but it also explains how my husband and I got it, as far as I'm concerned. These are 3 2.5-foot propane torch heaters. There were crowds standing in the sidewalk waiting to go into the outdoor restaurant between the indoor and the outdoor. We're at 181 up above, and we could smell the smoke. And we didn't know where it was coming from because nobody in our building smokes. And we didn't realize until too late. Okay, and our friend Tang of Orange Juice fame also very nicely talks about how smoke from a cigarette can disperse it, and odors from people's breath should be considered a risk factor, and so on. So you got to get stacks into moving airspace if you're going to get rid of toxic substances and not have them re-entrain. And I put in pictures of the building that won the AIA Code Award that I worked on. And it's a gorgeous building, just stunning. And this is the building, I did the specs for this is UMass Studio Art building. And this is where I teach the course. If you're interested in this field, if this at all interests you, and you have any interest also in theater or art, you might want to contact me about this course because it's a good introduction to a new phase for your career. It's 40 hours, so you have to be willing to listen to me for a long, long time. Local exhaust hood designs, as long as the physics of the systems are not violated, you can modify them. So these are the basic drawings. We modify, this is a welding table. This is the basic drawing of a slot hood. It always has to go into the duct at a 45-degree angle. You cannot vary that. That's a physics principle. So you need to go from the slot to the duct in a 45-degree entry phase. But you can modify that. So here's one for screen printing. Here's one for mixing of plaster. Here's one for a dye vat. This is a nice one. It's buried in the wall. And so you've got enclosure here. Here's another one of the same building, and so on. This is a foundry. We also use welding ducts for capture. And we now want to see that kind of negative pressure on all 3D printers, laser cutters, and so on. And where I'm going with that is here was one of the suggestions for the COVID patient. And of course, this is your takeoff, this little thin sucker here. So, you know, you're going elephant hunting with a pea shooter, but the principle is there. If you're really interested in ventilation for patients, NIOSH will give you, if you Google NIOSH headboard vent, it'll get you the plans for this. And so you can see there's your 45-degree angle, your gentle bends, your 30-degree entry, and your exhaust fan. Okay, now let's look at non-ventilation solutions. And this is, we'll start with UV first. And the most of us have seen UV cabinets for disinfecting safety glasses. You put them in there, and you'll notice they put the ones with the little black rubber thingies down at the bottom. Why? Well, because the bulb is up here, and reflected UV won't kill anything. It's got to be direct, so it can nicely go through these. But if it bounces off of one of these little rubber thingies, then it can't disinfect anything below that. So UV is limited in what it can do. In fact, the UV studies of trying to use it for N95 masks, because they're opaque, were not successful. So it has to be direct. This is just ridiculous. It can produce ozone in some cases, not in all, but in some. And let's face it, whether it's reflected or direct, it can cause skin cancer or eye damage in people. So this is not benign. Also, I'm a fellow of the American Institute for Conservation, and we don't want any kind of UV source wherever there's artworks, because it can dissociate bonds in pigments and things. So it can cause damage to a number of types of materials that might be in a museum. There's also these upper room systems where they shoot the UV at the ceiling, and then they think that this is going to kill the bug. I don't know if you've ever looked at a ceiling, but ceilings can have glossy paint that will reflect the UV down on you. It can have metal things up there like diffusers, and they bounce off. And they draw these nice arrows. And I can tell you that in your dreams, the air is going to do that. So I'm not in favor of these systems at all. And the issues with the UV duct, induct systems where you aren't exposed to it, I've put all of the reasons that you might want to rethink this. And you want to have manufacturers, third-party testing as installed, because these devices don't require EPA registration showing and proving that they are safe or effective. So it's buyer beware with these. And here's the AIHA statement, and they say it inactivates but does not capture the viruses, which is absolutely true. And it may be capable of reducing. This is. But your big thing is, once the pandemic is over, this system is no longer needed, and now it's a maintenance and potential hazard. But if instead you invest in good HVAC system, you've got an investment for life. What about ionizers, negative ions? We don't recommend any of these. None of them. The negative ion generators in most studies, I put this study in for you, 56 students were studied over a week long with ionizers, and their urinary concentration of a systemic oxidative stress biomarker was increased significantly. So those ions aren't good for you. They're just not. What is an ion? It's a species that is not electrically satisfied. It's looking for something to grab onto and react with. Ozone is the one that's more, and it is used to deodorize. What does it do? It rips up a double bond like this in a big solvent and makes it into two solvents. So you actually increase the amount of solvents with it, but many of the smaller molecules are less smelly, and some of them are more toxic. So you're not really getting anywhere with this. Here's pictures of the various types of ions, just the oxygen species. You can have nitrogen, hydrogen species as well. And the bipolar ionizers, this is from one of their ads. They fill the air full of negative and positive ions. I don't think you want to be in that damn room, you know, really. VOCs in the room can increase. Aldehydes like formaldehyde might be created. And I've given you studies to look at. And I really recommend you find this guy, Richard Corsi. He does a whole PowerPoint. We're not going to go through all of it in detail because we don't have time. But you really, really probably want to, well, here's where I've given you the study, and you can go to, it's a big long website, a webinar, but you just want to go to about 3/4 down and then just listen to this guy. And if you still want to use a bipolar ionizer when it's done, then I can't help you. And they may get away with it or they may not. This is a big lawsuit against one of the major manufacturers of the bipolar ionizer. And this, if you really want the data, I recommend you can just Google this and get a copy because it lists all the studies nice and neat at the bottom, okay? So now let's look again at other types of ventilation, and we'll look at the portable air cleaner. And this is from EPA's booklet in our country, and you can see they draw, I darkened this so you can see it. The air comes in here and goes out here. And I think they want you to assume that it goes up here and makes it all nice for the baby. Probably not, because this is negative pressure here, and this is positive pressure here. So these things usually develop circular air currents around them. So they're much more limited in pathway than you would think. These stickers that they have that tell you square feet, that's based on an 8-foot ceiling. Your schools don't usually have 8-foot ceilings. So you'd have to recalculate those anyway. So you don't want this CADR number they give you because it is a combination of CFM, which you do want to know, and filter efficiency, which you do want to know. So you just want to look on their site and find out how efficient their filter is and how many cubic feet per minute that it puts out so that you can figure out if you can use it. And ASHRAE clearly shows 3 of them in here and open windows because you're going to need a bunch of them. They don't make huge amounts of CFM, okay? Should we reopen the schools? Probably not. I have given you 3 studies that you can look at your leisure. This one really is a scary one. Re-examines the Texas experience. You know, you should have a visa to go to Texas anyway. I should. And here's another one showing, because the real problem is not in the schools often. It is the risk to the people living with a child who's in school. That's where your big risk is. So this plots that. So you might want to look at that study. In the New York schools, what a mess. They would put one cleaner in here, and this is not even a ventilation system. This is a heater. So they got nothing in here. This is how they actually tested to see if the vents were working. Toilet paper on a stick. Oh my, how advanced is that? And this is New York, okay? Then they've got the univents. Most of you have probably pushed pencils through that grate on the top. This is open and the shot inside, and this is the filter, and you can see the coil through the filter. You know, so get over it. This is not going to answer your issues either. And I've put in here a nice drawing to show you how they work. And this is if they're connected to outside air at all. Some of them they put in these rooms and they're not even connected. So they're recirculating through a crumbs and flies filter, and they're not really doing anything for you but heating and cooling. So I put the problems with the univents. Here is in New York, Mutt and Jeff taking a look at testing the univent. And this was the inspection reports that they put on the websites for all the schools in New York. And the first column here is there a window? Yes or no? Can at least one window open? Yes or no? Then there's 3 columns for supply fan, exhaust fan, unit ventilator. And whether their options are optional, partly optional, doesn't exist, can't access. Really? Really? My God. So if we look at Brandeis High School, which has 182 rooms, 42 of them don't have windows, and 131 of them have no operational supply fans. Some of them don't have operation. This is the number that's important. There's at least 131 rooms there that essentially don't have significant ventilation. This was taken by a teacher. The kids are sitting in their snowsuits pressed up against the heaters because they were relying on open windows. Third world, and it's New York. So there's a lot of problems with us as well. Here, we'll go back to this school. Here's a teacher. This is about the worst scenario you can come up with. This teacher's infected and is talking to the kids. And obviously, if there's no precautions, she can take out 12 of her students, something she's probably only dreamt about for years, but she can do it now. If they all wear masks, she cuts the number to 5. And then they say, well, there's good ventilation, which they picture as big, wide open windows and an open door. Then maybe she gives it to 1 person or 2 persons. Not really reliable. And remember, I put this in again because I want you to understand that they're not reliable. The New York Times then wrote a big one, right? This is the front page of the New York Times. Key to safe classrooms, open windows. But if you read the study, it says just the opposite. Amazing, amazing. They talk about 1 infected person in a room. And if you've got a window open and the circulation is going like this, your teacher's toast and probably a couple of the students are toast as well. So that's not an answer. And they say they only use this scenario under the specific weather conditions to get 4 air changes per hour. And they said to get to 6, which is what we need, we will have to do more. So here again, this study at least understands that specific weather conditions are needed if a window is going to work. And what they really were talking about is supply fans or exhaust fans in windows. So I commend this study to you as long as you understand the parameters. And obviously here they're using a window exhaust fan. They say that's best. But what if they remove, this is the infected person, and they put the infected person here, and your intake may be over here, because they never establish where the intake is. That's what's another big defect in this study. But this could just, take out the room. Here's our Department of Education. They said they recommend a window opening of 3 inches. Yeah. Not all windows need to be open. Classroom door can remain closed. Keep your reading. Really? Really? And the other thing they're doing is opening the old natural ventilation systems that were closed off in buildings. Well, there was a reason they were closed off. They don't go through a fire-rated chase. They go through walls. And the first thing we usually do on a renovation is make sure if there's any of these old ducts that they are blocked. But now they're opening them up. So if they're going to do that, I want to see a really good fire inspection by not your ordinary fire inspector who is looking at extinguishers, but somebody who knows these rules, because this could be a really serious problem. And since we're time-wise getting really, really short here, I want to make sure that everyone understands that a window air conditioner is no ventilation at all. Understand how a heating coil or condenser coil works. One end is hot and one end is cold. So they put the hot end out, blow a fan on it. The air from the room comes in, goes past the cold end, and comes back out. You do not have ventilation with an air conditioner. And so when you see a building that looks like that with no openings, except for these and windows, you don't want to put your kid there. I stole this one from the EPA ventilation. They said ventilation, if you fix the ventilation, you could also save money. because good ventilation will reduce sick days. And they've actually put a monetary number on that. And if you fix your school ventilation, you can improve test scores. And they say we've known that for 15 years, and they give you 4 studies there. If you want a bunch more studies, contact me. I'll give you, I got about 14 more studies besides those. So this is really well known that the fresh air also improves test scores. It's really a well-known fact. Carbon dioxide, on the other hand, will decrease mental acuity. And there are studies of both children and adults that will show that that's true. And in my business, where we have dry ice fog machines, we create enough to dull the intellects of actors and audience alike. Not a really smart move. Here's a study that I want to put in the study so you can look at it, because it's very clear that the virus was transmitted, and this was in September. So there was never any question that anybody should have not known it was the bug. Also, take a look at this study. This was studied repeatedly and was first done in January, published in January of 2020. And one person was infected. The air was going across, and we got a bunch of people infected. And this was all very well documented. The air was being blown from an air conditioner, hitting the opposite wall, coming back around, going through the air conditioner again, and circulating. Here's your tracer gas study of the same location. And you can see these people were in a backwater here of this virus. And this should put to rest once and for all the 6-foot rule, because these were 15.5 feet, 11, and so on. Even more interesting, they revisited this study just recently. And that was in May, they published this. And the reason they could revisit it is this was a birthday party, and the entire thing was videoed. And so they observed everybody's movements, and they recorded more than 40,000 surface touches and 13,000 episodes of close contacts during the entire lunch duration. And it allowed them to look at the infection risk from fomite and contact. And it just literally, this just doesn't agree. It doesn't show that this is a significant route. It's the airborne route that counts. And I put this one in because I like it. This is a 21.3 foot transmission in 5 minutes. That happened because the infected person was only overlapping in time with this person 5 minutes. So in other words, you can't, if you don't know the air currents, you can't know if you're protected. So forget the 6-foot rule. The further you are away, the better. I mean, that's good, but it isn't going to be protecting you. And if you plan to reopen a school, I do recommend you go to ASHRAE's epidemic task force stuff, because they have checklists for building readiness and equipment checks and so on, because your system has to work. But the rest of it, I have issues with. And you can look at their general advice, which I provide here, because now we know all the problems, and we can now just quickly go through the things that are really important. You need to know these 3 things. You need to demand that they tell you how many air changes per hour is in that room, what the filter efficiency is on the HVAC system, and the percentage of outdoor air that you're getting. Those 3 things. You know those, you know if you've got a reasonable chance of making it out alive. And the reasons for our choice of 6 is both AIHA and ACGIH say this is where effective engineering controls start, 6 to 12, 6 to 12. And even the ASHRAE position for healthcare is 6. And I put some other references there. So we decided on 6. ACGIH, this is their graphic, and this is where effective engineering controls be, and this is the relative risk reduction of these various things. And again, I'm going to take a hit at the Harvard Healthy Buildings. It says that 6 is ideal. No, that's minimum. That's minimum. So, you know, Good try, but no cigar. What is an air change? And here again, we got a formula about it. If you've had high school math, this is just easy. The CFM, that's cubic feet per minute that your ventilation is doing, times 60 minutes per hour, divided by the volume of the room. How simple is that? It's really not hard. What is an air change? You can mix the outside air change from your HVAC plus your HEPA control, HEPA filtering devices, and you want it to add up to 6. Now, 6 air changes doesn't mean that immediately the air is changed. It takes 46 minutes to get 99% effective removal in a room. So it does take time. And here's the tough concept. And I put this, this is the one that they keep quoting. I'm sorry, this is the one they keep quoting to me to say, we find increasing air change rate removes the virus from the source room faster, but also increases the rate of exposure in connected rooms. And that's what they've been telling me when they want to say, we don't want to do this. And I say, no, read the study, because they were working with a MERV 8, which, it doesn't stop the virus at all. So you're really, if they start with that on you, just tell them the only way that the viral load can increase in connecting rooms is if you've got a rotten filter in your system. So how does air changes control term? This is the difficult concept. There's a period of interest. And again, you want to look at our orange juice guy here, Tang. He says it as best you can, but if you can understand this study, you'll truly understand why we need to really start pretty much at 6 air changes, and why it's appropriate. Filter, you want to look at the effectiveness of that filter. For you people who know something about ventilation systems, your return must be ducted. You cannot use a plenum return, okay? And the efficiency ratings are this MERV, minimum efficiency reporting value. Heard that over and over, MERV. It's based on capture of a typical dust to protect the HVAC equipment. So that's kind of shaky. But now we have numbers and we can look at it. Here's your MERV 8. It doesn't collect anything in this range, and 20% in that range, 70%. So you can't use a MERV 8. So if you go up to the MERV 13, you've at least got 50% capture here and 85 and 90 over here. But your MERV 17, which is really not an ASHRAE standard, it's a HEPA, that is going to get 99.97% of everything, including your 0.3 micron particles. That's where you'd like to be. But MERV 13 is the limit. And I put this chart in because it's fun and you can play with it. MERV 13, so don't accept less. That's your bottom line. You may need to change out a motor or do something because it takes a little more static pressure in some cases to run these. But we have data from this study showing that it went through a MERV 15, so we know the bug will go through. Okay, then we have to look at outdoor air, how much you're flipping this damper over. And here's our minimum standards. Bingo. You can just, this is what we do when we're negotiating for a film location. The building manager gets this, and it's all at 6 ACH. This is the minimum standards. And it tells you if you got a MERV 13, you need 40% air. If you can't run a MERV 13 or better, you got to go to 100% outdoor air. Here it is. Bottom line, it's very simple. You hand it to the building manager. So air changes per hour, filter efficiency, percentage of fresh air, all important. How do we negotiate? If we're doing it with a good building, we get this. It's a big building. It's got all the air handling units by number, what they were designed to, and the actual measured CFM that they can produce, the volume of the room, the MERV filter, how many HEPA units they're going to need to get to 6, and then how far they got to 6. And there's your total ACH. And we could just look down this list and see, there's 3 rooms we're not going to use. Okay, simple. If you've got a good building manager, that's what happens. If you're only using 2 rooms, here's 2 rehearsal rooms, and they gave us the numbers, and we're at 8.2 and 8.29 air changes. And this is all through a HEPA. So, I mean, you know, we can do this. This is the instrument you don't want to measure ACH with because it measures at a point. What you want is this device. This is called a bolometer. You just put it over the supply, or in this case, you put it on the intake side of things. This is on an univent. Once you have that CFM number, you just plug it into this. You take that reading from that bolometer times 60 divided by the volume of the room, and you get the air changes. You can do this. And if you can't do that, if you've got a handheld CO2 detector, you want to shoot some CO2 into the air and let it, you take some fans and get it circulating. As long as you get a nice steady CO2 reading, you want to take a reading and then wait 15 or 20 minutes and then take another reading. And then you plug it into this formula. CO2 at the end minus ambient outdoor, CO2 at the start minus ambient, and you don't even have to measure ambient if you don't want to. You can just assume it's 400. And then you need, unfortunately, -1 times the log number of that solved. And you just type it into Google and boom, up comes the number, and you divide it by the hours in, and you've got your air changes. It's just, man, I'm of the slide rule era, so you know you've got nothing to worry about here. Creative use of these standards, we actually develop ways of ventilating trailers with HEPA filters and air conditioning units. So we can actually do anything. We can ventilate any place. These are the HEPA units. If we're going to do a big place, we got little ones. We got 20,000 CFM units. We got everything. You can just rent this stuff, you know. And who says all this? These people say it. Here again, I'm going to keep pushing these sets of standards. We're sticking to them. They've been working for us for a long time now. And other information that you can get from us, if you want a union-oriented list of contract demands before negotiating indoors, we can talk. Here's a list of proposed design changes, because last week I lectured to only architects and engineers. So if you're one of those people, this might be something that you begin, and it has specific recommendations for theater, house, stage, and orchestra pit. Slide ventilation, issues for bathrooms. Boy, Lord help us with bathrooms. And information on the course that I'm teaching. So if you're interested in any of those things, you know, you can contact me. If you can spell my name, you can find me. I'm so easy to find. I haven't hidden from anybody in years. So let's talk. Let's see if we've got some questions. And we can just make this happen. Okay? Mr. Moderator, I'm done.
Well, Monona, thank you very much for a unbelievably factual, direct, and inspirational presentation. Ladies and gentlemen, there's a lot of information there. We're going to take some questions, and you know, there's a lot of questions coming in. We're going to try to concentrate on the primary ones, and I'm going to start it off, and then Gabor, I'm going to hand it off to you. And let's start with the first one. And I had this question as well. I refer to it as the plexiglass mania. Everybody's got plexiglass going up everywhere. You kind of addressed it. The actual question that came in was, well, what about the banks where they've got the tellers and these huge plexiglass screens? I guess the comment was, well, they put it high enough, then you can't have the aerosols going over. We ran into the same issue with an installation we recently had done, in which all of the salespeople carousels were all formed into these little individual plexiglass jungles. that intuitively indicated that we're blocking the airflow. Sounds counterintuitive. What do you say? What do you say, Monona?
Yeah, you got to sit down with the mechanicals. You got to see where your diffusers and your returns are. And then you go floor to ceiling and make sure you have a diffuser and a return separate on each side. So you may have to even shut off something, change something. You may have to, be manipulating and rebalancing that room. But floor to ceiling is the only way to make sure that you're not having it just going over the top.
So I would assume that if you are utilizing, for example, portable HEPA filter systems, you will got to be strategic in terms of where you're putting them, because you want to make sure that the inlet is in the right place and the exhaust is in the right place.
Yeah, that, and you want to be sitting on them. You want to be right as close to that HEPA as you can get, because that's where your maximum ventilation, your maximum filtration is.
Gabor, next question.
Someone's comment on that very subject. Not only does the plexiglass trap the pathogens, but it actually impedes any proper ventilation system.
Absolutely.
You talked about airflow, and the plexiglass is impeding it.
Yeah, because that's why I said, and in fact, what I told the architects and engineers last week is that we can no longer plan in 2 dimensions. We have to plan in 3, and got to look at where the airflow is going and make sure we don't put any structures, not only plexiglass, but equipment that is impeding that airflow. So it has to be worked out better than we've been doing.
Okay. Monona, I told you I wouldn't give you easy questions, so here's one you're going to have to chomp on. Open or close schools?
You don't do either. You can open the schools that have buildings that will support this activity. You have to look building by building, and that means classroom by classroom computation of the air changes per hour and whether or not it's going to be a safe place to be, or at least low risk, because I don't like to say safe anymore, but low risk. So anybody who says open the schools doesn't get it, because I think half of the schools in New York should have been closed before the pandemic. They weren't safe before. So, we really need to look at an environment, one building at a time.
So I would presume that what you're saying is just sticking technical appliance A on the wall or on the floor isn't going to cut it. You're suggesting there has to be an assessment in each and every individual room.
Yes, and I just saw, and I won't tell you just where, but there's a proposal, and it looks like it's going to go through here in New York, and they're going to be putting ionizers in a whole bunch of these rooms. And remember, the ionizer cannot capture the virus. It can only electrically make it want to stick together and stick to surfaces, including sticking to you. This is not what you want the virus to do. They say that the ion is so reactive that it inactivates the virus, but that's debatable. And you really need studies of these systems to show that that's what's happening. So, I mean, this is just crazy. They were just willy-nilly saying, we'll put one of these in each room and now it will be safe. That's insanity.
I would suggest that if the ionizer is that powerful that it will deactivate all the viruses in a classroom, it's going to deactivate a lot of other things in the...
Including your lung cells.
Yeah, absolutely.
All right. Well, thank you. Because, Monona, there was a lot of information there. We're getting close to the time, and I've got the producer whispering in my ear. We're going to have to wrap it up right now. But let me just make a couple of summation points here. We're now at the end of the session, obviously, and I'm going to just summarize to try to keep it all simple, stupid. We're going to try to put this in the context of rather simplicity, as opposed to all of the very technical issues that you've gone over with us. I would suggest, and these points I've run by Monona to see if she's in agreement. I didn't want to misstate what she had said. We're left really with 4 key points here. The position stated today is that only schools that can be safely, or we've used the word air safely or safe airly, opened, should be open, and the benchmark is to meet or exceed the various standards which Monona went over with us today. Number 2, the key here is to achieve fresh, clean air that is as clean, fresh, and pathogen-free as possible. And I think I mentioned previously that we're not going to achieve a eradication here. We're going to use best practices, best technology in order to achieve the best possible scenario we can, and keeping in mind also, economic reasonableness of it. Number 3, aerosols, airborne aerosol spread is the primary route for COVID transmission, particularly in, and you've heard these words over and over and over, particularly in closed, crowded, poorly ventilated indoor spaces. Monona has already trained you with the lingo. That's what we said she was going to do, and she's also told you what your demands should rightfully be, i.e., demand the achievement of the minimal benchmark standards that Monona today has suggested. And she went it over and over and over again, and she said, 1, ask about the filter efficiency. Number 2, ask about the ACH, the air exchanges per hour. And number 3, inquire about, well, how much fresh outdoor air are we bringing into this particular room? What you learned today applies with some degree of scalability and retrofit for almost every indoor environment. However, each environment is unique in its own ways. There is no cookie cutter solution. There are only some specific principles which Monona has done a great job of eliciting and explaining to us today. Please watch for the fact sheets that will be issued subsequent to this presentation. And the presentation itself will be posted online, probably on my LinkedIn feed, probably on the Novametrics LinkedIn feed. I know that some people had difficulty getting online because of the number of people. We apologize for that, but this is really something that you got to sit down and spend some time with, because there was an awful lot of information that was provided to us today. Finally, a special thank you to all of the people who have made this webinar event happen. All have provided their time, energies with no expectation of compensation. Mea culpa to Monona Rossol, our guest speaker, to Dr. Gabor Lantos, and to the people behind the scenes, Dave, Vicky, and the Bktb's collaborative partners at Novametrics Research. Before you leave, please note that you can again join Gabor and me on Thursday, July 29th, which is 2 days from now, at 11 a.m. as we assume the position of lead speakers at another online Safe Air webinar, which has been tailored for the pharmaceutical industry. The pharmaceutical industry presentation focuses on sustaining and creating a safe and sustainable return to air-safe environment in the pharmaceutical sector. That seminar is being hosted and presented by Safeopedia and is titled Achieving a Safe Workplace in a COVID Environment, Ventilation, Remediation Necessary to Abate Airborne COVID Transmission. Watch my LinkedIn feed for the link to that session. Again, thank you very much to all of you for joining us today.